Hello everyone. In this topic, we are going to discuss superconductivity in detail. So first, much before the superconductivity was invented, the general rule, the general belief was like this. The conductivity of any material is due to two things. One is because of the phonon scattering, which is temperature dependent. Look, the phonon scattering. The phonon scattering, which is temperature dependent, and the impurity dependent, right, which is independent of the temperature. And it is represented as the Mathesian's rule. It is represented as the expression given here. Here rho is the resistivity of the given metal and rho I is the residual resistivity due to the impurities, and rho pH is the temperature dependent, and it is also called phonons. Phonons are quantized lattice vibration. So in general, if you plot a graph, the graph will be like this as shown here. Look, the graph is shown here. So if you take temperature along the x-axis and the resistivity along the y-axis, the resistance will come like this and it will become non-zero. So this is what generally happens. But later, when it was in 1911, the entire game got a twist. It was in the year 1908 where HK once liquefied helium. Then he started to work on the resistivity, on studying the resistivity of mercury, and he identified that at 1911, right, at 1911, the resistivity of mercury suddenly dropped to zero. Look, at a temperature of 4.2 Kelvin, mean near absolute zero, the resistivity of mercury drops to zero. So the belief of the previous belief of the temperature dependence due to the impurity and the temperature resistance due to the temperature has to be proven to be wrong. So now let's discuss about superconductivity. So the resistance offered by certain materials to the flow of electric current abruptly drops to zero below a threshold temperature. So the particular temperature where the superconductivity occurs or where the resistance becomes zero is called the superconductivity. Then the particular temperature, in case of mercury it was 4.2 Kelvin. So the particular temperature where the resistance dropped to zero is called the critical temperature. Right. So superconductivity, the resistance becomes zero is superconductivity, and at what temperature the resistance becomes zero is the critical temperature. Then so comparing the non-superconducting materials and the superconducting material. So for a non-superconductor, the graph will become non-zero at 0 Kelvin. But whereas for a superconductor, the temperature will slowly decrease and then suddenly it drops to 0. So this is what happens in a superconductor. So the critical temperature, which is also represented as Tc, is generally very low. So for aluminium it is 1.2 Kelvin, and for mercury it is 4.2 Kelvin, and look at for lead it is about 7.2 Kelvin. And for silver it is 0.001 Kelvin. I mean it's less than 0.001 Kelvin, and hence it is considered non-superconducting in nature. Next, a small note. We know a magnet will be having magnetic lines of forces, and the lines will be initiated from north and end at south. Initiated from the north, and the magnetic lines of forces starts at the north and ends at south, right? And now these magnetic lines of forces will pass through all objects. These magnetic lines of forces will penetrate through the objects. Now, phenomenon observed by Meissner, and it is called by his name, the Meissner effect. So in 1934, Meissner and Robert discovered that an external magnetic field is perfectly expelled from the interior of a superconductor. What does this mean? That means if magnetic lines of forces are expelled at that particular temperature, that material all of a sudden becomes diamagnetic in nature. That is, the susceptibility, the magnetic susceptibility is -1. Okay, here a comparison of the Meissner effect. So now if a superconductor is kept in magnetic field and the temperature is maintained a little above the critical temperature, then the magnetic lines of forces will pass through the superconductor. Look, the ball shaped superconductor, let us consider, and if we keep this superconductor in magnetic field, let B be the magnetic field, and now the magnetic field will pass through the superconductor. And now if suppose, look, here the temperature is greater than the critical temperature, and now if we decrease the temperature, when the temperature is less than or equal to, we can make less than or equal to, if the temperature of this ball is made to less than T less than or equal to critical temperature, then the magnetic lines of forces will be expelled by this material, and here we can call the material is becoming perfect diamagnet. So at normal state, the magnetic lines of forces will pass through the superconductor, and in the superconducting state the magnetic lines of forces will be expelled, and this is what we call the Meissner effect. Done. So here look in a slide showing, here we have an magnet, and above that we place a superconductor. Above that we place a superconductor, or vice versa, we can have a superconductor here or we can place a magnet here, it will be the same. The effect, the resultant effect will be the same. So look, then there is something called a critical field. So we know the critical temperature, and there is something called the critical field. So let's see what happens if we increase the magnetic field of this magnet. So here let's assume this is the magnet, and here we have the superconducting material here. So what happens if we increase, let us assume the material is at perfect temperature Tc, I mean the critical temperature, and now if the magnetic field of this magnet is slowly increased, we are increasing the magnetic field of this magnet slowly, and when the magnetic field reaches Hc, when the intensity of the magnetic field reaches Hc, then this superconductor will no longer behave as a superconductor. Simply magnetic field destroys superconducting phenomenon. So here, to be precise, Hc is the critical field that can be handled by the superconductor at 0 Kelvin. H is the magnetic field that can be handled by the superconductor at 0 Kelvin, and at Tc is the critical temperature. So the relation between the critical field, that is the critical field that can be handled by a superconductor at temperature T, is given by this equation. So Hc0 is this value, and 1 minus T by Tc square. Tc is the critical temperature and T is the given temperature at any given temperature. So the other thing called the Silsby effect. So we know a current carrying conductor will produce magnetic field, or we can say magnetic fields are induced by current. Whenever a current is flowing, then we will be having some magnetic field. So here, if we increase the current, we know the magnetic field will also be increasing. So at a particular value of IC, at a particular value of the current, the magnetic field reaches Hc. Am I right? The magnetic field reaches Hc, and this magnetic field will destroy the superconducting phenomenon, and this effect is what we call Silsby effect. So it can be defined like this: the maximum amount of current that can flow through the superconductor without destroying the superconducting state is called critical current. So here there are different types of superconductors. We have two types generally, type 1 and type 2 superconductors. So for type 1 superconductor, if you plot H and the susceptibility along H along the x-axis and susceptibility along the y-axis, we'll be having a graph, a perfect triangle. The red colored curve is for type 1 superconductor. So you'll be getting a perfect triangle. So with H, the M is increasing proportionally, and all of a sudden at a particular field called Hc, this material will become a normal conductor. But whereas coming to the type 2 superconductor, if we increase the magnetic field, then M will slowly increase, reaches some value, and then it slowly decreases. It slowly decreases and traces this way, traces this path. So instead of just going and abruptly dropping to zero, this slowly increases, and then decreases. So here, coming to the type 2 superconductor, up to here we can call it as perfect superconducting state, and from here to here, we call it as the mixed state, and again above this Hc2 we have the normal state. Look, for a type 1 superconductor we have only one Hc, whereas for a type 2 superconductor we have two Hc, so we name it as Hc1 and Hc2. So in simple terms, a type 1 superconductor will be having only one critical field, whereas a type 2 superconductor will be having two critical fields, and hence we name it as Hc1 and Hc2. So what happens here? We will check. So here a type 1 superconductor, it expels magnetic lines of forces, and when it comes to this point it allows the magnetic lines of forces to pass through. But whereas here, look, the mixed state, so some filaments are allowing the magnetic lines to pass through. Look here, some filaments are allowing, but some part is expelling, and that is why we call it as mixed state. It has an other name too, called vortex state. And then the normal state. So look, this superconducting state and the normal conducting state is common both for type 1 and type 2 superconductor. So coming to type 1 superconductor, it behaves as a superconductor up below this, and it will behave as a normal conductor above this, but it is different in case of type 2 superconductor. Here look, the blow up of the type 2 superconductor, that particularly in the vortex state. So let's consider the material is in the vortex state, and look, there are some filaments. Look, the normal state course. So we have the normal state. So here in this state, the material is allowing the magnetic lines of force to pass through, and we have some superconducting region. So and this is why we get the mixed state, the vortex state. Vortex in the sense, some places it conducts and some places it does not, and hence the name vortex. Look, is can be represented by this diagram also. Look, the differences is given here. The type 1 superconductors are otherwise named as soft superconductors, and the type 2 superconductors are otherwise called hard superconductors. So soft is type 1 and hard is type 2. So the soft superconductors are those which can tolerate impurities without affecting the superconducting properties. So they can tolerate little amount of impurities, whereas these hard superconductors cannot tolerate impurities. Impurities in the sense, if you dope something, then the superconducting behavior will be collapsed in type 2 superconductors. Here in type 1 the critical field is low, and in type 2 the critical field is high. Low, high. And then in type 1 superconductors they show complete Meissner effect, and here they will be showing complete Meissner effect up to one stage, and then mixed effect in one stage, and then the other part a complete expulsion in the other state. So here the hard superconductors trap magnetic flux, and hence Meissner effect is not complete. I mean, in the sense, this happens in the vortex state. The current flows through the surface only. If you pass current through an type 1 superconductor, then the current will flow only through the surface. And then in type 2 superconductor, that current will be flowing throughout the material. Inside and outside, throughout the material it will be flowing. An example is Examples are tin and aluminium, and here you can remember an example as niobium. Niobium is a type 1, type 2 superconductor, and tin is a type 1 superconductor. The other example for type 2 is tantalum. Here we have the list of known type 1 superconductors, the material and its corresponding critical temperature in Kelvin. Look, the name of the materials, their elemental symbol and their corresponding temperature is given below. The material and the corresponding temperature. The material and then the corresponding temperature. This is just for your reference. Look, among them, look, niobium. Look, here we have, this is type 1, and here, as I said, no, look here, niobium is type 2. Known superconductors. It's not known type 1 superconductors. Then the BCS theory. So now we have to account why such a thing can happen. How electrons can flow only in a superconductor without any resistance. So that was given by three scientists, combinedly accounted by three scientists. We call it as BCS theory. Barden, Cooper and Schrieffer. And it was awarded a Nobel Prize in the year 1972, and the theory was proposed in the year 1957. So here, so we know electrons are fermions. We call something as fermions, the spin half. So now, this Cooper, they realized that the electron, instead of behaving as fermions, they are behaving as bosons. Bosons in the sense the spin zero particles. How come it be spin zero? That's the next case. So now, how can we get a boson spin zero from spin half? In the sense, let's consider two electrons, one spin half and the spin minus half. If these two electrons combine, then we'll be getting spin zero particle. So keep this in mind. And now let's start the explanation now. So Cooper realized that atomic lattice vibrations force the electrons to pair up into teams. So look, one electron one electron is pairing up with the another electron through the lattice vibration and this lattice vibration is called the phonon. So here the pairing will be more if the positive spin electron and the negative spin electron, so this electron is supposed to be having positive spin and here this electron must be having a negative spin, then these two electrons will be paired up and this pair is called Cooper pair. So the attractive force necessary for such a state is being created by the exchange of phonons. Look, I have explained here the exchange of phonons, in the sense phonons are lattice vibrations. I am repeating, phonons are lattice vibrations, quantized lattice vibrations. So thus the lattice act as a media for the attractive force between the two electrons. So here during the flow of current, if an electron is passing through the lattice, then the lattice ion move towards the electron. Then the next electron get this energy back from the lattice and hence one electron is giving the energy, is leaving some sort of energy to the lattice and leaving. And the next approaching electron from below gets that energy, and now these two electrons are considered to be paired up and the source of interaction is lattice phonon, or simply we can call it as phonon. So this type of interaction is called electron lattice interaction. Then the interaction between the two electrons happens via the phonon field. This interaction is called electron lattice electron interaction. Thus the two electrons attractively interact. Look, one electron attracts the another electron and this is called the Cooper pair. So the points are getting repeated. It's getting repeated. The first, in the sixth point, the fifth and sixth point explains about the electron gives the energy and leaves. And here the seventh and eighth point tells the leftover energy of the electron in the lattice is transmitted to the another electron. So the electron lattice electron interaction, and this is what we call the Cooper pair. The energy of the bound state is less than the energy of the free state. So the energy, the bound state energy, so the Cooper pair is called the bound state, and here the difference is less. I mean the bound state energy is less when compared with the free state energy, and this difference is called binding energy of Cooper pairs. If the temperature is less than the critical temperature, electron lattice electron interaction is stronger than the electron electron Coulomb interaction. Right. So here this pairing up is possible one and only below and equal to the critical temperature, not above that. So if you cool down the material when the temperature is nearby, is equal to the critical temperature or less than the critical temperature, here the lattice interaction will dominate the Coulomb's repulsion and the electrons will be paired up, and here the Coulomb pair is formed. So here these Coulomb pairs act collectively. They act collectively rather, and thus they will behave as a giant quantum state. So they will act collectively. So all this Cooper pair will move with uniform velocity. So the velocity of the Cooper pair will be uniform. So the possibility of scattering is too small and hence there is no resistance at all. And this is how the lattice vibration happens. Look, one electron is pulling the another electron. Look here, two electrons are passing by, one behind the other or one over the other we can consider. And here the electron is distorting the lattice. Now the electron is distorting the lattice and the lattice is moving back to the normal position. So here the Cooper pair formation is shown. The Cooper pair interaction with the lattice is shown. Next, one of the important application of superconductivity, the magnetic leviated vehicles, simply maglev vehicles. So here we have an big guided rail, a big guided rail, and here beneath the carriage, beneath the cabin, we have a superconducting magnet, and here we have the wheels, and these wheels are retractable. So just it works like an airplane wheel. So here we'll be having an aluminum guide. Beneath here we'll be having an aluminum guide, and this aluminum guide, in this aluminum guide we apply magnetic waves. So we know the magnetic wave, the magnets, whatever the magnetic field, east or north or south, the magnetic field will repel the superconductor. No, the magnetic field will repel the superconductor. So instead of just applying a simple magnetic field, we apply here a magnetic wave. So if the magnetic wave is traveling, so this traveling wave will push the magnet, will push the superconducting magnet, and hence the it will be moving, the carriage will be propelled. So once we are supposed to stop the train, so the field here is slowly reduced, the speed of the field here, the wave here, the magnetic wave here is slowly reduced, and hence this will be slowly slowed down. And what happens, suppose if the carriage has to be stopped, then the wheels will be again coming out, and now these wheels will be resting, the carriage will be resting on the wheels. While the carriage is propelled, if they are moving, there will be a gap here, and if it is stopped, this wheel will slowly settle here on the carriage, on the rail. Done. Any questions if you have, you can ping me.